So, so yesterday we have covered the topics broad plot, larger phase margin. I think, yeah. Yesterday we have covered broad plots, like phase shift minus 20 minus 90 degrees, average block to phase for field plot. So gain margin and phase margin. These are basically measures of next is gain margin and phase margin. Gain margin and phase margin. These are basically measures of how close the system is to instability. Think of them as safety margins, gain margin. First, remember what we said about the Nyquist critical point. Minus plus plus J0. This is imaginary equation. So here J0. For instability, here this is critical point. We are particularly interested in condition magnitude equals to 1, phase equals to minus 180 degrees. So this is the Nyquist criteria, critical point. Magnitude equals to 1. For instability, we are particularly interested in magnitude equals to 1, phase equals to minus 180 degrees in dB. So 20 log 10 of 1 equals to 0 dB. So one on the board magnitude plot, 0 dB is important. Phase crossover frequency. Find the frequency where angle of G of j omega, H of j omega is minus 180 degrees. This is called phase crossover frequency, omega PC. Then look at the magnitude of the frequency. Suppose U of j omega PC magnitude equals 0.5 in dB, 20 log 10 of 0.5 base 10 equivalent to minus 6.02 dB. The system is 6 dB below the dangerous 0 dB level. Therefore, the gain margin is approximately gain GM equals 6.02 dB. Institution gain margin tells you how much I can increase the gain before reaching the instability boundary. So larger gain margin means more safety against gain increase. More safety means it adds safety uh, for not gain increasing. So how much I can increase the gain before reaching the instability boundary. Phase margin. Now look at the opposite situation. Find the frequency where magnitude of g omega, g of frequency. J omega means frequency. Here omega means frequency. J means phase. Okay. J represents phase. So G of frequency, H of frequency equals to 1 or 0 dB. This is called the gain crossover frequency, omega GC. Then look at phase. Suppose at the frequency, angle of G of frequency, H of frequency equals to minus 135 degrees. The difference between the dangerous phase is minus 180 degrees. So here we get minus 135. So the remaining safety is PM equals to 180 minus 185. This is dangerous phase. So suppose we got the frequency minus 135. So we by differentiating, so, so look at this diagram. A Bot plot stability margins. So this diagram looks confusing, but look at this diagram. Its x-axis are both same for both magnitude and phase, but for y-axis it is changing values. For y-axis magnitude is minus 60 to 40. For x-axis it is minus 2. For phase it is minus 270 to minus 45. So this is the magnitude to frequency graph. This is one graph, and phase this is one graph. These both are not same. Okay? These both are different, but here in this diagram they both look similar. So for 0 dB, we particularly want to 0 dB and minus 180. So we draw a horizontal line for 0 dB and minus 180 degrees for both magnitude and phase. So then we look at where the horizontal line meets the graph at of magnitude to frequency. Then we draw a vertical line towards the frequency x-axis. Same we do to then We measure the minus 180 to here it comes exactly approximately minus 100 like that. So minus 180, so from 180 minus 100 means plus 100. It is thus minus 80. So 80 is the phase margin here. If you look at the second vertical line, the second vertical line, we look from bottom to upwards. So from 180, minus 180 here it's actually a line, a graph. We put a point and we draw a vertical line. It touches the second graph of magnitude. Then we draw a horizontal line. And the distance between the 0 dB horizontal line to this line is gain margin. So the derivations definitions is given measured at phase margin, measured at gain cos of frequency. This is gain cos of frequency. Is the amount by which phase is above minus 180 when the magnitude is 0. When the magnitude is 0 dB, phase is above 180 is the phase margin. For gain margin, measured at the phase crossover frequency, omega pc, it is a factor by which the gain can increase. If the gain can increase by factor by which at minus 180 phase, at minus 180 phase, it is a gain, but it can increase uh, system to become unstable. Sorry. It is a factor by which gain can increase in dB at minus 180 phase before the system becomes unstable. It can increase before it gets unstable. So this is gain margin. So for stability, phase margin is greater than 0 and for gain margin is greater than 0 dB. Phase margin is greater than 0 degrees. Phase margin is greater than 0 degrees and gain margin is greater than 0 degrees. Gain margin is greater than 0 degrees for stability. If I understood the diagram. Here, here see, we got here we got asked the question what is LMG? Here it is a minus one of the between real and imaginary. Imagine if this and this is no encirclement of minus one closest loop table. Uh, Figure point one minus one plus j is now j0. The root pass where at the root from the circuit. So this is forward path, this is feedback path. If you read control systems, you will know what is forward path and feedback path. Okay. Um, so what is minus 1 point? Here T of x equal to g of x will under g of x into h of x. The denominator is under g of x into h of x. So this is transfer function. Okay. Closed loop transfer function formula. Why do we calculate transfer function for closed loop or open loop? We say transfer function like let's cover open loop and closed loop. Here. It tells the system's ability to uh, transfer it term. It tells about the gain by output by input ratio. Yeah, the transfer gives us exactly the relation output by input, the zero initial conditions. Why use this? Instead of describing everything directly in time, we use abstract transform. So everything is therefore y of x is x of x equal to 1. That's much easier to work with. Why is the useful for control system? Stability, force endurance, frequency response, lot loss, gain margin, phase margin, transient response, open loop transfer function. So transfer function means input the output. G of S is the system. Uh, if there is no feedback, this is the transfer function for C of S by R of S is transfer function. If there is a closed system, then it will change. This is forward path, this is feedback path. G of S equals to H of S. Forward transfer function is C of S by R of S equals to G of S by 1 by C of S into H of S. This equation is extremely important. While G of S equals H of S is important, look at the denominator. The system becomes problematic when 1 plus G of X into H of X equals 0. Therefore, G of X into H of X equals minus 1. And this is where exactly y equals product and the critical point minus 1. So now you can see the connection transfer function clear in the equation 1 plus G of X into H of X. So H of X is a feedback path. You can see for a closed loop system, desired output feedback goes to input again. We have subtracted from the output. Uh, so this is G of X into C of X by R of X. C of X means output, R of X means input. You see, this is input. Their feedback is connected to the system only, but it is their input is also going, though it is connected to system. But we say G of X into H of X, because G of X by C of by R is equal to 1 plus G of X into H of X is the formula. Why is G of X equals to H of X important? Suppose this is 0, this becomes 0. If this becomes 0, then this is problematic. Why this is problematic? If denominator becomes 0, what happens? Exactly, that is the right question. But there is one factor. The transfer function becoming mathematically input doesn't mean the physical system will ever produce input altogether. It means the mathematical model says the system has reached an unstable condition. Recall, G of equals to 1 plus G of X and H of X. If 1 plus G of X is equal to H of X, the definite denominator is 0, which tends toward infinity. But why does that mean instability? Think about the feedback loop. Normally, negative feedback reduces the output. Output feedback opposes input, system settle. Okay, but at the critical condition, G of S equals to H of equals to minus 1, the signal going around the loop has magnitude 1. It means if we do magnitude of this, we get minus 1. We get 1. It comes back with the same side, phase minus 1 again. The negative feedback subtraction effectively turns into reinforcement. Signal feedback opposes signal. We effectively got signals feedback and input signal to signal. The signal can keep producing itself. A simple analogy, imagine a microphone placed near a speaker. Normal speaker or sound microphone. If the microphone picks up a little sound and sends it back to the speaker, you may hear the sound keeps reinforcing itself. That analyzes the feedback reaching the critical condition. Why does the denominator matter? The closed loop poles are determined by 1 plus g of s into h of s equals 0. So when this equation has a solution, the right hand of explain the response contains a growing exponential and becomes unstable. At the exact boundary, poles can reach the imaginary axis, produce sustained oscillation. So don't memorize denominator for more attention. Instead, remember the data answer GFX and HF is equals to closed loop. And the equation of that pole determines whether the system is stable, marginally stable, or unstable. Yesterday, studied stability. We we get the if there are equation depending on the equation. If we solve the equation, if the values uh, changes, then there are um, two RHS values to The right hand side values we have studied yesterday. Those are unstable values. We have studied instability and stability yesterday. So this is the transfer function. So we get minus. Why we get base minus 180? Let's ask why we get base minus 180. The phase minus 180 is not something we arbitrarily choose. It comes from an empty feedback structure. What does minus 180 the phase shift of minus 180 means the signal is inverted. Originally we send this. After 180 the signal is inverted. Mathematically E of G of this is Euler's formula minus theta minus 180 equals minus of j theta. So a minus 180 phase shift is essentially a sign reversal, but our feedback is already negative, right? This is negative feedback, right? That's why it reverse the whole, and that's why we get minus 180. So there are so many open loop formulas, like E means error. It is calculated by input minus feedback into output. The feedback, the feedback signal is subtracted. The subtraction itself is equivalent to multiplying the feedback signal by minus 1, which corresponds to 180. Now imagine the loop itself adds another minus 180. Suppose g of is equal to h of s has a phase of minus 180, then the signal coming back to the loop is already inverted. So that's why it is minus 180. Because of the feedback to reinforce the original signal, loop must provide a necessary phase reversal. The loop condition is g of x equal to h of x plus minus 1 minus 1 equals to 1 angle of minus 180. Therefore, g of magnitude of h of x and angle of h of x. These together gives the critical condition. Think of an amplitude. So that's it. The amplifier property phase shift is 0. It comes to amplifier. The feedback sign and the phase shift G of J omega H of J omega are separate things. Negative feedback always produce minus 180. So we use negative feedback for open loop system and closed loop. In control system, we use negative feedback. The reason 180 is the critical point in space of standard negative loop and loop space inversion and to cancel explicit negative sign in the feedback path and in the feedback effective into reinforcement. And that's why bot plots watch specifically for minus 1 and Eclipse watches specifically for minus 1 of June. Okay, that's the minus 180 scale. No confusion. Oh, where are we? Yeah, this is where we gain margin. So this is Nikish criteria. We got magnitude 1 case because of negative feedback we get minus 180. If we substitute in for 20 log 10 base 10, this is we solved bot plots using this type 20 log 10 log of 1 base 10 equals 0 dB. We see here bot let's continue next topic. 16. Lead lag compensation technique. The compensator is basically an additional circuit or controller added to a control system to improve its performance. Think of it like tuning the system. R equals to C of x, R towards C of x, C of x is connected to G of x, G of x are to output. The compensator here feedback is both getting going to the system. CFS means this is output. CFS means compensate. Okay. CFS is compensator. The compensator is basically additional circuit controller. This is additional circuit controller added to a control system to improve its performance. This is lead compensation, lag. Mainly use lead compensation, lag compensation, lead or lag compensation. Read and lag compensation. Why do we need compensation? Suppose a control system has problems such as slow response, poor stability margin, large steady state error, insufficient phase margin. Instead of completely redesigning the system, we can add a compensator. So compensation equals to modify system behavior to improve performance. So compensation is nothing but modifying the system behavior for the input to improve the performance of the whole system. Why do we need a compensation? Is a slow response. Suppose this is system have problems like very slow response, very poor stability margin, means no stability at poor stability, large steady state error means this is one kind of error, insufficient phase margin. These are all leads to instability, right? That's why for that we use a compensation, modify system behavior to improve. Lead compensation. A lead compensator is mainly used to improve transient response and stability margin. In simple terms, it provides positive phase contribution over a useful frequency range that can increase phase margin. So lead compensator is used to improve transient response. We read about transient response, like forced response, and stability margin. In simple terms, it provides positive phase contribution over its transient response, steady state, forced response, natural response equals to forced response plus uh, complete response equals to forced response plus natural response. The transfer response comes under means forced response. Transient means there is a state between what we say from transient response means transient state, steady state period. Transient state means from initial conditions from 0 plus to infinity between the conditions it is a transient state. So it is in transient. Here transient response means improved transient response and stability margin. We'll look into this later. A typical lead compensator of the form C of s equals to k into 1 plus Ts by 1 plus infinity Ts, where 0 is less than infinity is less than 1. We don't need to memorize the design equations here. Institution without compensation. Without compensation, this is a slow response. With lead compensation, this is fast response. So think lead faster, better phase margin. Compensations. Lag compensation mainly would improve steady state accuracy. It can increase the low frequency gain related to the high frequency behavior, helping reduce steady state error. Think lag is better steady state accuracy, but it generally introduces additional phase lag, so it is primarily used to improve phase margin. Lead lag compensation. As the name suggests, it combines both lead, improve transient of stability, lag, improve steady state accuracy. Therefore, lead lag improve both steady state, transient and steady state performance. Next, I have completed all this, but we have to study. I am very confused with some thoughts here. Steady state accuracy. Yes, your understanding of transfer is correct. The important thing is the same idea applies to control, but now we are talking about output response of the whole system, not just a capacitor inductor. In RC circuit, you already saw switch on initial condition capacitor transfer response. Final values, for example, VC of equals to V into 1 minus V for minus V by RC. The changing portion of the transient eventually VC of T equals to V, so it becomes steady state. Some same concept in control system. Suppose you suddenly give a motor its desired speed. Desired speed controls motor's actual speed. Initially, the motor might respond transient state, steady state. The path where the output is changing toward its final behavior is the transient response. Once it steadies, steady state response. So this is a DC, but same constant applies in control system. So for desired speed, we want to go in a particular speed, and to control the motor, the actual speed means desired speed minus actual speed, output speed will go feedback as to the input again. So this feedback happens for when it comes to steady state. This region is transient state. So once it states a steady state response. So what's the difference with combination? This is where the terminology we just use. Lead compression mainly improves transient. For example, faster response, better damping, reducing overshoot, improving force margin. So it improves transient response, means it reduces transient response. That's why we get a faster response, steady state. Mainly improves steady state response. Uh, Suppose we said steady state not changing. It's a good, but technically steady state response doesn't necessarily have to be constant. For example, the input is sinusoidal, the steady state output can be sinusoidal, transient dies steady state sinusoid. So more totally transient temporary behavior that dies, steady state behavior that remains after the transient has died. Okay. 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 So um, here lead compensation makes the response faster. So lead compensation increases the time for transient response. That slows down the system response rate. You get steady state response faster. Lead composition does the opposite. Lead composition generally makes the system respond faster. Think of step input. So steady state here, this is transient response is period while output is second. The lead composition mainly works to enter the transfer, often by increasing system parameters, increasing phase margin, making the response. Potentially reducing excessive sluggishness. So simpler memory lead faster time, lag better steady state exist. Faster doesn't mean zero setting time. A lead composition can make the system work. Lead increase transient time, lead improve the transit, generally making the system more responsive. Lag improves the steady setting usually at the cost of some speed. Okay. We use lag, don't worry about speed, cost of some speed is reduced. So lead and line compensation is our transmission line equation, propagation constant, optimal study, transmission line, water transmission line, some coaxial cables where electromagnetic waves travels through them, which were caused by this AC signal with higher frequencies. Due to that higher frequencies, change in electric signal, change in magnetic signal occurs, and the magnitude is exposed. Usually, information is going to them. So transmission line equation, primary and secondary parameters, open and short circuit lights. This is simply open and short circuited license. Uh, the ends of the transmission line, if it is infinite, suppose if it is open at some part, then current is if it open, then resistance is more. More resistance means higher current, lower current. Voltage is max. Voltage is max. Normal current. That's using that condition we calculated some propagation constant and standing wave equations. Sorry, reflection coefficient equations are there. VSWR means voltage standing wave ratio. Impedance matching. We calculate something propagation constant of things on which tells us what happens when mm, it will eventually give some equations. Open. Short means if the circuit is infinite, it goes infinitely, then there is no resistance. Suppose no resistance, that means current is max, voltage is low, something like that. Using that, we will calculate propagation constant. It tells us standing waves. The meaning of standing waves means it was standing waves are problematic for transmission lines. It is like a disturbance happens for transmission lines. So in reflection coefficient, the reflection coefficient means when the transmission lines are going to receive the receiver, uh, probably some load is there. When the load going to the load, if there is a reflection, that creates a standing waves. That creates the standing waves, which is the problem. The reflection coefficient equations are this. We will continue with this one. We'll continue that. I think we'll continue that.